Okay, happy Friday, everybody. Thanks for joining. So this is the last part of the tutorial series organized by the Year of Remote Sensing Committee, supported by DOE through the AmeriFlex Management Project. And we're excited to hear from Nicola Falco, who also works at Lawrence Berkeley National Lab, telling us about analysis of remote sensing data. Take it away, Nicola.
All right, thank you, Christine. I hope you can hear me well and see the slide that I'm sharing already.
Yes.
Okay. Today we will look at a little bit of some processing analysis, some quality control, and some application. I just wanted to give a couple of words on what has been, what we have been seeing so far. We started with the first tutorial looking at what is remote sensing, what is a remote sensing system, and I won't go into detail, but just to remind people what a remote sensing system looks like, right? We have been discussing the electromagnetic spectrum and the properties of certain wavelengths to describe vegetation properties, for example. We have been digging a little bit on vegetation indexes and what vegetation indexes can be used for specific purposes. For example, we have been seeing the NDVI is the oldest, was the first one, is the most widely used for several processes to characterize several processes. There are several others that have been used to improve, for example, some issues with the NDVI, for example, saturation and so on. And EVI is enhanced vegetation index is one of those. We also saw that, for example, STIF is a new, let's say, solar induced fluorescence is a new metric that we have been recently started to use, also because the advancing sensors technology allow us to really go much higher spectral resolution to really capture those photons at a certain wavelengths. And metrics like SIF give us better understanding of even dynamics on photosynthesis, for example. We have been with Josh. I saw Josh on the call today. He has been giving a really nice overview of current and future missions that are focused on earth science, right? Going from water to land to temperature and to topography, and so many different sensors are coming out and put on satellites, platforms, or on the ISS, or available even for airborne or even drones, right? The second tutorial was looking at where do we get this data, right? There's different platforms where people can go and select the data set that they are interested in and download over areas of interest, right? NASA has its own portal where they do pre-processing and some processing of some of the data. Google Earth Engine becomes also one of the most widely used platform where basically we can see and find most of the open data available out there. So that has been and it still continue to be a super valuable resources. And in the last tutorial from Gilberto went through a discussion on FluxNet and what are the products and the quality assessment, which maybe not everyone knows about it. And so the take home message from last week was that it's really good to better understand what are the data that you're looking at, and also, dig a little bit more how they are being produced, but also if there's any quality control that you should be aware, and to really increase, to make, your process more efficient, right? And here we are with today, going back to the remote sensing system, right? So which is the process of detecting and monitoring the physical characteristics of an area by measuring its reflected and emitted radiation at a distance, right? So typically from a satellite or aircraft or a drone. And so we have spatial sensors and camera that collect remotely sensed images or signal, which help us to sense things about Earth, right? Now, the value recorded at any pixel, for example, pixel location on a remotely sensed image does not really represent the true ground leveling radiance at the point, right? Part of the brightness is due to the reflectance of the target of interest, while the remaining is actually derived from brightness of the atmosphere itself, right? So the system is really complex. It's not like taking a picture down Earth and really get a clear picture. There's a layers of there are several layers of interface where signals go through, get reflected, and so on. And so what we see at the satellite is a portion, or is actually the all these components put together, right? And so the separation of the different contributions is not known a priori, and so there are different steps that allow us to correct this and correct the final signal and account for all these contributions. So the next few slides, I want just to go through a little bit of what are the correction in pre-processing of remote sensing images. And I want to go through this so people can understand what are actually the steps that we need to be sure about it that has been done before even computing the NDVI, right? And so, yeah, there are several steps where different correction and calibration are needed. And so sensors in general record the intensity of electromagnetic radiation as a digital number. And so the first step is to convert this digital number to meaningful physical units, such as radiance, reflectance, or brightness temperature. And usually sensors specific information are needed to carry out this calibration process. So in a decade ago or so, if you were downloading a Landsat image, you by yourself needed to apply some of this conversion from the digital number to the radiance, and then from radiance to top of atmosphere or to at sensor reflectance, right? So, but now such routines are more integrated in the system, but not all the systems are carrying these routines. The next step is atmospheric correction, which is the process of removing the effects of the atmosphere. And this process basically to produce the surface reflectance values. And so atmospheric correction can significantly improve the interpretability and use of an image, and ideally this process requires knowledge of the atmospheric conditions, aerosol properties, and the time of acquisition. Now, so if you have all this information, then one way to do this is using atmospheric models that account for the effect of the scattering and absorption of the atmosphere. And there's a number of parameters that are required to accurately apply atmospheric correction, including properties such as the amount of water vapor and distribution of aerosols. Many software's packages include also atmospheric radiation transfer model that can estimate it through surface reflectance. And so here are listed, for example, Motran and Flash, which are probably the most used model for this kind of processing. In case that all this that information is not all available, there are also empirical approaches. And one of the methods is, for example, the empirical line method, which uses reflectance of dark and light object measured on the ground to create then a linear model to transform radiance or the digital number recorded at the sensor to the surface reflectance. Now, this, of course, involved ground data collection. And, you know, you can see someone having a big tarp on the ground, different color from black. Maybe you can have a black, and then you have a white, maybe you have a gray, you have a field spectrometer on the ground and collect the data over these areas or targets while you have your, or close when you have a satellite or airborne or flying over, right? So this, you probably don't need only two values, you need several values and so several acquisitions, right? And so that become also a demanding process. But nevertheless would provide kind of good quality transformation. Now, other issues in terms of quality that people should be aware or is, for example, stripes and that pixels, right? So here, for example, we have a figure of a ET map which was estimated using Landsat 7. And Landsat 7 is known for having these issues of stripes, which is due to the scanline corrector failure, right? So now the striping approaches are available in the literature and provided by the scientific community, and can be found also in software such as MV. And so this, for example, is one issue that someone should know about it, right? Rather going on Google engine and blindly downloading, I don't know, 20 years of Landsat 7, then discover that you have this problem and you have one of these stripe over the pixel you are interested in. So this is also something to be sure about. Other quality control are related, for example, removal of data errors or flaws. I think like in this category falls also clouds and shadows. There's, for example, in this slide, you can see a couple of scenes from Eco-Stress where the white areas is basically masked using a cloud mask, which is provided. And so basically we can use this kind of product to mask unreliable land surface temperature estimates, right? Other type of correction involve geometrical corrections, such as georeferencing, which is operation to give each pixel geographical coordinates. And this operation will stretch, scale, and rotate the original data, right? And to basically adjust to the real dimensions, basically. Another operation is auto-rectification, and this step is needed to correct, for example, distortion from sensor tilt and the earth terrain. And this process requires more information than georeferencing. Generally, to auto-rectify a raster data set, you will need an accurate digital elevation model. And for example, I put here an example of airborne hyperspectral that was that after being stitched together and georeferenced, we still have issues in alignment and with some distortion, right? And so we see, for example, that the river doesn't really continue. There's some area where they break down, and there's like some shifts here and there, right? So going back and rerun auto-rectification, looking at if the DEM has issues and so on. This is you know, a very intensive process to really have final really high quality data. And you know, after all these steps, we might be able to start, you know, to do some real analysis, right, of the image, and for example, computing the vegetation indices. I just wanted to mention that in general, most of the satellite provide, most of its providers that are based on satellite platforms would give you a already georeferenced surface reflectance product, right? On the other hand, providers of airborne-based products and drones not always have these capabilities for such operations. So that become, you know, something that the user needs to look into, discuss what could be the procedures and so on. And sometimes the user needs to collect data on the ground to be then integrated with airborne data. Right. And in the next slide, I want to show is also that some of these, you know, satellite providers, for example, Landsat, have also quality attributes. And so Landsat, for example, have band reporting cloud quality assessment. So it shows you what would be, what could be the cloud coverage and radiometric saturations and also aerosol information. And for example, all the Landsat families has these quality flags, for example. I also recently data sets, for example, again, EcoStress or JEDI has also flag systems for the same purpose. And so people can really look into what if the area that you're looking at has really meaningful data or should be masked, right? So from the next slide, we will focus on some more application of remote sensing data. And we would start, for example, linking remote sensing to fluxes. So we have been seeing in the previous tutorials how you know, we use vegetation indexes to predict GPP or other fluxes, or how they are integrating models for the same purpose, right? I think like there's a couple of challenges when we are looking at this data, and for example, how to really integrate the remote sensing. For example, if we look at NDVI into the flux data, right? So there are a couple of things to think about: the time component and the spatial component, right? So from the time perspective, imagine that you have, imagine to have the dynamics here shows in this figure of the CO2 uptake. And this is an example from a small crop field in Arkansas. While you have hourly data, your NDVI from Landsat, for example, as a revisit time, which is about of 2 weeks, right? And so the first problem we see is that although we have 2 weeks of revisit time, that might not be enough to capture relevant dynamics, and not enough if you have only one or few years of data. And we are talking about, you know, weather is always nice in this case, right? But, you know, that is not true. So it won't be 2 weeks all the time. We also think about that NDVI, for example, in contrast to SIF, right, require a structural change in plant tissues before showing a detectable change, right? So even linking NDVI daily to a flux data, right, daily, that wouldn't really change much, right? The NDVI wouldn't really show any detectable change between 1 or 2 days. Probably will start maybe starting from a week. It really depends on what biomes we are looking at. And so one thing that people start to do, and because, you know, availability of new satellites that are really overlapping, have similar acquisition conditions and pixel resolution, is to combine different satellites. And for example, if we combine Landsat 8 and Landsat 7, we probably start to have data much more often, right? Like probably down a week or so. On the other hand, right, this kind of operation always need a sensor-to-sensor calibration, right? There's always, sensors are not the same. There's always some issue, like there's always some differences in how much energy a sensor is detecting. And so calibration between sensors are needed when they are fused together, and then to look some, you know, physiological or phenological vegetation properties. And in fact, here we see that there are some differences from EVI compared to from Landsat 8 compared to Landsat 7 across a different part of the growing season. So going back to the time component, question that we're thinking of is like, what are there any lag effects between fluxes and DVI? Is there a preferential integration window? And so if we look, for example, the CO2 fluxes at different time of the day, right, and we correlate that to NDVI, we see that there is mainly two regions of highly correlation, day and night, right? Because we can really see a separation from uptake and respiration, right? And so if we do that, similarly, if we do that for the various fluxes, we can see, for example, the time window of the day for the day that could be optimal for each single fluxes. And see here, for example, I plotting the correlations between NDVI over 2 years of data between different fluxes, including CO2, methane, air temperature, and evapotranspiration, right? And additionally, what we would also need to understand is the integration time. That is what I was mentioning before. Because NDVI doesn't change much in a few days, what would be the time, the window integration, the optimal window integration for fluxes, for example? And so here there's an example of going from 1 day integration, like getting the average of the fluxes at a specific optimal time, to 5 days of flux integration. And here we see that slowly, the correlation between, for example, NDVI or EVI, which is even better, between EVI and CO2 is increasing, right? And so, this couple of slides just shows you the kind of I guess, preliminary analysis to understand when we can really link flux data to the remote sensing metric that you're using. This may be work for an NDVI, other indexes may be different, and also depending, right, on the biome you're looking, right? If you're on a forest, if you are on a crop in Arkansas, you know, dynamics is very different. So there's no really one way to go, right? This has to be investigated. So the other component, as we mentioned before and in the previous tutorial, is the spatial component, right? Changes in fluxes are highly dependent on the land cover and wind directions. The common method is to select a pixel that are near to the tower location. Now, if we are using, to do that, we always need to be sure that the pixel size basically should cover at least the majority of the footprint, but that is not always really the case, right? If we want to start to compare different sites, we see the different spatial scales, right? And so and the other point is that we also want to understand and account for the spatial variability inside of the footprint, right? These footprints are over areas that are rarely homogeneous. And so in this case, the moderate resolution, for example, MODIS, can be insufficient for capturing the fine scale spatial variation in fluxes, right? So recently there are some studies, and there start to be there's some also tutorial where maybe a better way to do is basically integrate remote sensing and the fluxes by weighting the remote sensing metric by the contribution of the flux, right? And so for that case, you would need high resolution data, right? So maybe airborne or even satellite. For example, now we have a planet. They have been out for at least since 2016 or 17. There are some years of data. Pixel is at 3 by 3 meters of resolution. Daily acquisitions, so from the temporal resolution is great. We can start to use high resolution data to really characterize the spatial heterogeneity inside of the 2D footprint, to then use a weighting approach to basically better integrate our remote sensing metric and link it to the fluxes, right? And so here, I just wanted to put a couple of pictures, images from this NEON tutorial that was given last year. And this is a really nice tutorial that shows you how to link, for example, the raster data from NEON airborne hyperspectral to the print of their tower, and how weight the NDVI based on the distance of a line computed over the 2D print of their tower. And so that is a nice tutorial that should be very informative to people. With the next slide, I just going through a couple of applications where remote sensing, why remote sensing can be linked directly to the flux, right? But it can not only that, can also provide information on the ecosystems, right? Properties. And for example, land cover map is one product that people start to be using to see what is the spatial heterogeneity, how different land cover contribute to the total flux, and so on, right? So ecosystem characterization, right? So landscape properties such as land cover, soil composition, geology, topography, hydrology, and climate influenced by geochemical processes, and therefore the carbon water cycles, right? And so these kind of processes can be observed using observing platforms, right? So we can derive proxies using sensing technology, and that can provide information and can inform on such biogeochemical processes. And so land cover analysis and species mapping, right? So when we are looking at fluxes, or in general, if you are interested to understand what is the spatial variability on land cover, or plant functional type and vegetation, right? Global land cover products such as the USGS map, or the most recent Copernicus global map at 10-meter resolution could be sufficient to investigate this spatial variability, right? If we are interested to understand the forest no forest variation, for example, or forest, grassland, and urban. This kind of global land cover products. The positive part of this global is that they are consistent across the entire globe, right? The drawback is the course of the information providing at the class level, right? You maybe want to understand what kind of forest do you have there, and maybe you want to see some variability across grassland, like meadows and shrubland. This kind of thing, right? So once has to think about, okay, how can I go more deep and to get to higher information on that aspect? And so for more granularity, airborne hyperspectral has been used also to obtain high resolution map dominant species and plant traits. And so here is an example. You see the three scenes one is from Google Earth Engine, right, RGB. The middle is this Copernicus global map, and the last one is basically hyperspectral based classification map of dominant species, right? And so these two land cover maps really give you a totally different granularity of the ecosystems, right? And depending on how is big your area that you're investigating, one or the other could provide you better information, right? And so if you are doing that, there's all a process, right, where extensive ground data collection is needed to get at this granularity. High resolution in terms of spectral range is needed to basically to discriminate different plants, right? And then most of the time we have some post-processing, some processing that look into how to extract the most informative information from hyperspectral. While hyperspectral images are very informative, right? They can become very heavy to process at, for example, 1 meter resolution from neon dataset. And so techniques such as principal component analysis, independent component analysis, or other techniques that are able to compress all the information and get rid of redundant information can be then used in a machine learning approach to then provide this kind of a product. This could be like a general approach for that kind of task. I remember one question was given in the first tutorial. What about, apply these techniques to then link to actually estimate fluxes, for example, or other physical metrics? We always need to remember that every time we do processing and we transform the data, we go from the physical meaning of the data to something else that most of the time is not relatable anymore, right? And so really depend on the task you're looking at. This kind of transformation, give you good results. In other tasks, maybe it is less meaningful, and it might be better just to stick with the full range of wavelengths, or just collect the wavelengths that are more informative, rather than transform completely the data. Another part of the ecosystem characterization is, for example, landscape property and topography. LiDAR being providing topographical measurement of elevation, slope, aspect, and you can identify ridge and depressions. We know that, for example, in agriculture fields, depressions are really important to understand where there's water accumulation, and there's an impact on the crop and the plant developments. And then, of course, that would cause like a spatial heterogeneity of CO2 fluxes, right? Here I'm showing, for example, a study on topographical heterogeneity, which in Alaska, I think. And here, for example, LiDAR and then a clustering methods to basically understand what is basically the spatial variability, and so identify areas that have similar topographical properties are linked to variation in carbon fluxes. And so understanding how the landscape was changing was actually providing insights on the carbon cycling in these ice wedge polygonal regions that are quite typical in Alaska, for example. And so to write it up, this is the last slide, since we are approaching 9:40, and I would want to give some time for questions and discussions. So remote sensing images require several pre-processing steps before being operational, right? And so satellite-based acquisition are in general already corrected, but imagery acquired by airborne and drone might need user intervention. And so it's really, I think it's really good to, at least to be aware of these processes. And knowing about the remote sensing data properties, issues, and possible quality assessments, for example, the Lancet quality flag or EcoStress, or different product from ISS as the same flag systems, will really help in avoiding and considering unreliable data. So really, optimize your time on that. And then, remote sensing data are very helpful in providing ecosystem landscape information that can be integrated in your analysis for flux quantification, and can be used to then improve the understanding and prediction of biogeochemical processes, which all are linked to carbon water cycles. And so with that, thank you very much, and we can open the floor to questions.
Thank you, Nicola. Yeah, let us know if you have a question. I think it's a small enough group. If you want to unmute or put something in chat, maybe people are furiously typing. Nicola, do you know what's next for the committee of the Year of Remote Sensing?
So maybe here Josh can also help me. I think like there's a workshop being organized for summer. I think we have been also discussing of having people coming to provide seminars on different missions, current and future missions. And so there are some activities that we are trying to organize for this year, definitely. And we will always keep the community updated, and through emails and Twitters, and of course the Ameriflux website.
I'm going to stop recording for now.